this is not the second homework review. Instead, this is going to be the first homework preview. So instead of reviewing last week's homework set, I'm going to preview this week's homework set and accordingly publish those videos earlier so they can help you with the homework. The reasons are, one, that it means you don't have to, think about, am I going to spend an hour or two watching stuff from the past when I'm also trying to keep up with the stuff we're doing right now in the course. And instead you get to watch something that will hopefully help you with the homework and therefore allow you to complete the homework faster. Second reason I think this is a good idea is that I think it makes the homework sets less intimidating. They look fairly long, even if often a large number of the questions is actually fairly fast, right? So those 25 or 30 questions, it looks like a lot of them tend to be fairly fast if you stick with it, but it still seems somewhat intimidating, and hopefully just taking apart some of those questions in advance is going to help you tackle the homework set. The final, and for me obviously the most important reason of all, is that it means I don't actually have to work the problems all the way to the end. Because I'm not going to. I'm going to look at a problem, analyze it, discuss the concepts that matter, set it up to some extent, but you will have to actually finish it. That means I don't have to ever get out a calculator or anything like that. That is going to be entirely up to you. So, 3 good reasons to go from homework reviews to homework previews. This is the chapter 24 homework preview, and the problems I'm going to look at are 11, 14, 16, 21. Those concern flux for the most part, and then 42, 46, 54, and 60. I initially had 43 on the list, but that is a problem that's essentially identical to the situation I discussed in my video on Gauss's Law part 2. So instead I put problem 60 on the list, which is not actually on the homework, but it is a problem that involves a non-uniform charge density. So where the amount of charge per cubic meter or cubic millimeter isn't the same everywhere. The problem like that is not in your homework. It requires you to actually perform integration kind of situation. So I'm going to do it here in this video, or more likely the second part of this video. Video 2, if you like. Okay, let's get started. So here's the situation for question 11. And I ask you that you open your textbook or Mastering Physics to look at what those problems are, so that I don't have to read them out to you. You don't want to listen to me just read the problem. That is boring. But here's the problem, right? You've got a sheet, or you have a flat sheet, and through that sheet there's an electric field. It's represented by those red arrows. And we're told what the total flux is. The total flux is 25 Newton meter squared per coulomb. Right, so newtons per coulomb, that is electric field. Meter squared is area. So you've got electric field times area. That is indeed what flux is. So you remember that flux, the definition of flux, right, is defined as phi E it's really the integral, right? We're summing up all the tiny chunks of area of E dot dA. That is generally true. The integral is taken over the area through which we want to find the flux. In the case of Gauss's law, this is a closed one, but the flux is just defined like that for any area. In this case, it's not closed, it's just this sheet. Now we look at this, and the neat thing here is that the electric field that we want to find, right, the magnitude of this electric field, it's the same everywhere. We don't know what it is, we only know its direction, but we know it's the same. So that means this expression for flux really just becomes the electric field that now doesn't depend on where you are. It's just one vector value dot product with the area. If you want to be sort of more formal, you could have the intermediate step where you take E out, the integral, and then you just take the integral over this dA, summing up all the tiny little bits of area, but all those little tiny sort of mosaic pieces of the total area, they all point in the same direction. I've represented that direction by the flag here, the flagpole that shows us the orientation of the area. And so this integral is just going to give me back the area, which has a unique direction, namely up. I know what the value of this is. I sort of know what the value of this is, right? You can figure this out. It's a rectangle, 20 centimeters, 10 centimeters. I want to find E. The one thing I have to be aware of, though, is the angle, right? Because the dot product is E, like the magnitude of the first thing, that's the thing I want to find, times the magnitude of the second thing, and the magnitude of the area vector, that is literally just the area. The area in how many square meters is it, times the cosine of the angle between them. Now, what is the angle between them? It says here 60 degrees. But be careful, notice that the angle is defined as the angle between the orientation of the surface, which is represented by my little flagpole, and the direction of the field. So in this case, the orientation of the surface, if I draw another flagpole, say right here, right, it is not 60 degrees, but it is this angle here. This is my theta. Now at this point you just have to plug in, solve for the area, beware of the units, write this in centimeters, but you want to express it in meters because the flux is ultimately expressed in meters squared. So you need to convert those. But then you can just straightforwardly solve for the electric field. And that completes question 11. So let's move on to number 14. I had to pause the video and then try to draw it. I did an awful job the first time around. So here's my next attempt. I think it's still pretty awful. It's just incredibly hard to draw those kinds of things in 3D. But here's my attempt. So the setup is that we have a circle and we're given the radius. The radius is, well, given the diameter. The diameter is 3 centimeters, although you might have a different value. You can figure out what the radius is. I'm just going to call the radius of this circle, I'm going to call it R. I'm going to draw it here, doesn't matter. This is supposed to be a circle that's lying in the XZ plane, right? So I've got 3 axes, they're all perpendicular to each other. This is in 3 dimensions. Try to visualize it, right? You can imagine this. If I have an x-axis, a y-axis, and then my z-axis sort of sticks out in the 3rd direction. And that circle, that area, is parallel, like this, the z and the x-axis, they lie in the plane of that circle. Alright, so you could sort of draw the axis in 3D space, and it goes right along the surface of the circle. Same thing for z, and the y-axis sort of cuts right through it. Here's a sort of front view, as if we are looking from the point over here along the y-axis. The y-axis sort of sticks in like this. Try to visualize it. Make sure you understand what the setup is. And then we're told we've got this electric field that's given by this expression here. Now the first thing you want to do is you want to decipher what that means. And I hope you've seen the IJK notation. It's just to say what is the x component, y component, z component. right? The I is the unit vector in the x direction, so we're saying for 1500 units of electric field in the x direction, 1500 units in the y direction, and then minus 1500 in the z direction. It's just, a way you might have written the same thing as 1500 minus 1500. It'd be exactly the same thing, just written differently. Okay, what does it look like? Now, I'm not going to attempt to draw it because I'd make a terrible job of it. At least the field is uniform, right? It's the same everywhere, but so it is a positive x direction. So if I look here, the field goes in the positive x direction, in the positive y direction, the negative z direction. So, okay, I'm going to attempt this. Imagine I go 1500 units this way, 1500 units in the x direction, and then 1500 units down. But of course, if I try to do the arrow like this, you can't really tell what's going on. Is it next to the x? No, it's meant to be sort of diagonally down, right? Imagine you stay in the xy plane. Imagine like a big sheet is the xy plane. It goes diagonally between the x and y axis, and then you go down. It's really hard to draw this, right? So we are asked to find, if this is electric field everywhere here, so I could sort of draw similar arrows everywhere, what is the flux through the surface? So if you can visualize it, right? Okay, that is something, right? That is a good start. Now, we know that flux, right, is defined as, well, the integral, but just like in the last problem, the field is constant, the surface is flat, so the flux here is just this area times electric field, the dot product between electric field and area. Doesn't matter which way around because the dot product is symmetric. So I know what this is, and I know it's a circle of a known radius, so I can figure out what the magnitude of it is. So what is the vector? Let's figure that out. The vector that represents the area, well, if the area is flat in the zx or xz plane, then if I stick a flagpole into it straight out, it's going to stick out essentially exactly along the y-axis. Right? I could draw it anyway. I could draw it here too. It would just be like confusing, right? So the area everywhere, the direction sticks out in the direction of the y-axis. The y-axis is perpendicular to the surface, right? So my area is only going to have a y component and nothing else. Let's write this down. A is going to be equal to the magnitude of A is just the area of this circle. So you can figure out what that is. Area of circle, because you know the radius, and again make sure you convert to meters. We get something in meters squared. And then we multiply that by the vector, right? This is the magnitude. The vector, the unit vector, the direction is going to be just in the y direction, so I can write it like this. Right? 0, the flag does not at all point in the x direction. It does not at all point in the z direction. It only points in the y direction. And we can fill in what the magnitude is. That is just the area. How many square meters is it? So now you have the electric field and you have the area. Now you just have to take the dot product. Now one way you could do this is geometrically. You could find the angle between them, right? And maybe you can just sort of see this, what it is. I'm not going to tell you, but maybe if you've got a strong enough 3D visualization, you might be able to see what the angle is. But let's do it the other way. I'm just going to literally work out the dot product the way I know how dot products work, right? So to actually just evaluate the dot product, I multiply each I multiply the two vectors component by component, and I add. So it's EX AX plus EY AY plus EZ AZ. But that's a general expression for dot product between two vectors. And if you want to know the angle between, say, two vectors in 3D space, it's actually a good way to find it, because you know dot product is equal to the magnitude times cosine of the angle between them. You can use that to find the angle. That's not what we're doing here. We know what those two are, and we just want to evaluate this. So we want to evaluate this this expression. Now I'm given the electric field, right? Is the x component, y component, z component, or you know, in IJK notation, x component, y component, z component. But the area, right? Those two, AX and AZ, are 0. So this is actually 0. The only thing you have to worry about is this. So you multiply the y component of this by the y component of this, and that'll get you the answer. Right, so we're actually working out the dot product here, the way you hopefully have learned it in some math course in the recent past. And that gives you the flux. But as I said, if you can sort of spot what the angle is between them, and you got to visualize this in 3D, you might be able to do it via magnitude times cosine of the angle. Actually, I think this method is easier here. Okay, so that was number 14. On to 16. In number 16, you're asked to find the electric flux through each of the two cylinders, one part A, one B. The cylinders are identical, but the electric field is subtly different in the two cases. So we're looking at this whole cylinder, and we're asking what is the flux. Now this one we can actually just solve conceptually. Electric field has some value E. We're not given a value. We're asked to express our final answer in terms of the magnitude of E and the radius of that cylinder. Now what you notice is that none of the field lines actually enters the cylinder on the round part of the cylinder, right? The only places where field lines enter the cylinder or leave it is at the end. Now, because all those field lines are parallel to each other, that's part of the setup that we're given, that implies that the number of field lines going in on this side is the same as the number of field lines going out on that side. Right, it's just perfectly uniform field, and we just put our cylinder bang in the middle. Now you could work out what is the flux through here. You find the area of this in terms of the radius. You multiply it by the electric field. You take the cosine of the angle between them, which in this case is easy to do, because remember the flag, right, of the area would sort of stick out like this, right? The angle is 0 between the area vector, the orientation of the area, and the electric field. You could work it out, the flux through this, and then the flux through the other side. But because any field line that goes in here comes out the other side, you already know that whatever the flux is here, you're going to get minus that answer on the other side. So what's the total flux? You figure it out. Part B is somewhat different. So part B is sort of this funny situation. You have to look very closely. The electric field is also all parallel to the cylinder, but on the one side it goes to the left, on the other side it goes to the right. So the way you might get that, I suppose, is if you had, say, a big sort of sheet of charge, of positive charge in the middle. Like a sheet of charge sort of placed like my pen is right now. Something like that might give you that kind of electric field. Sheet itself isn't shown, we don't care, we're just told, look, this is what the electric field looks like. So in this case, right, the field lines come out here, the field lines come out here, so the flux has the same sign in both cases. And usually the flags are defined as pointing outwards from our closed area, right? The whole cylinder is a closed surface. Can't look inside. There's no way for the insides to spill out. So you have your flags. The angle between the flag and the field is again 0, and this time the directions align on both sides. So you actually have to figure out what is the flux, but it's easy. It's a constant electric field, 0-degree angle, and you just work out what is the area of this surface here. Then you remember that you've got two of them, but they're essentially identical, so whatever the flux is that you find for this part here, you're going to just multiply it by 2, and that is going to get you to the answer. Pretty straightforward, just to do with understanding what is flux, how does it relate to electric field and area, how do I define the direction of an area, and so on. Should have no trouble with this question. Here's the next one, number 21. This one is a little bit different. It asks us to find the flux through that cylinder, and there are 3 charges. So we're not seeing the electric field here. We're just given the charges, and there are 3 charges. There's a plus 100 nanocoulomb charge. That's to the left of the cylinder. A minus 100 nanocoulomb charge to the right, and a plus 1 nanocoulomb charge in the middle, and that last one is inside the cylinder. And even the textbook or Mastering Physics has to tell you, look, this is inside, right? Because it's hard to draw in 3D. When you have diagrams, you're trying to see what's inside and so on. Okay, so we don't know the electric field. We don't know the distances involved in any of this, right? We don't have any dimensions, so we can't really calculate the electric field either. So what we do have, though, is Gauss's law. And Gauss's law states that the total flux through a closed surface, and this cylinder is a closed surface, right? Again, the plus 1 nanocoulomb charge can't fall out. There's no way to reach in. You know, the lids of the cylinder are there. They're part of the surface. So that is inside, whereas the other 2 charges are outside. And Gauss's law says the total flux through the closed surface is equal to charge inside divided by epsilon 0. That constant that determines the overall strength of electrostatic interactions. Now, if you were to try to draw the electric field, this one would sort of hardly feature at all, because those ones are way bigger. For every 100 field lines coming out of this one, 1 field line comes out of this one. So you'd hardly see this one on a field line diagram. But we don't need to draw it, because any field line, right, that comes out of this one and enters the surface is going to leave it again. Doesn't matter where, we don't have to worry about the shape of it, but any field line I start here, maybe it'll go to infinity, maybe it'll go to the minus charge and end there. Doesn't matter. If it enters the cylinder, it's got to leave the cylinder. If it doesn't, well, then it doesn't contribute to the flux anyway. So this one doesn't contribute at all to the flux through this closed surface, because any field that enters it leaves it again, and so those 2 contributions would cancel out. The same thing is true for this one, right? Any field line that ends up here and goes through the cylinder, enters the cylinder somewhere, comes out of it somewhere, I don't care where, but I know that the entrance and the exit, they're going to cancel out. One gives me positive flux, one gives me negative flux. So the only thing that I'm actually concerned about is the charge inside. These ones, they're just there to confuse you. And so I can apply Gauss's law, and Gauss's law does not care about charges outside. In this case, I can't use Gauss's law to say calculate the electric field. It is not a symmetric situation. I don't know enough about the dimensions here, but what I do know from Gauss's law is what the total flux through this surface is going to be. So remember, Gauss's law says electric flux, yes, it's defined as the integral of E dot dA, but we also know that is equal to the charge inside divided by epsilon 0. And that'll give you the answer. That's all we need. Okay, that's it for the first video. I'm going to continue with question 42 in part 2 of this homework preview. I'll see you in video 2.